to use SLE techniques to obtain some estimates about percolation. So the main goal today will be to finish the proof of the thing I stated yesterday, which is the following. If you take critical percolation on the hexagonal, on the faces of the hexagonal lattice or on the triangular lattice, so the one for which we know that we have convergence to SLE6, the goal is to show that the probability that the origin is connected to the boundary of a box of size n, so the probability that the diameter of the connected component of 0 is larger than n, that this behaves like n to the minus 5/48 plus little o of 1. So that's the goal, is to obtain this statement and to see how this is related to SLE and how we can use SLE to obtain the values of this. So this 5/48, this is known as a critical exponent because it's an exponent and it describes the critical behavior of a system. So just one remark before we start. You might think that, so what we know, the main ingredient, so the main fact, is that the probability that you cross a rectangle by a lattice of mesh delta, for any given shape of a rectangle, you know that this has a limit as delta goes to 0, which is some function of the rectangle. So if this is 1 and this is lambda, it's some function of lambda. And this function is very explicit and is conformally invariant, so you might think that already inside this f, you might be able to find the value of this 5/48. For instance, if you want to go from 0 to this boundary, you might build this example out of crossings of rectangles and try to be smart about it, and out of this, extract the value of the 5/48. And as far as I know, it's not really possible to do it directly, but of course, proving convergence to SLE6 is done using that, and then once you know that you converge to SLE6, then you can derive the value of the exponent.
Are you in the half plane or in the?
This is in the whole plane. There is no boundary. Okay, so before I go into the link with SLE, let me define just one more exponent which will be a little bit easier to compute and to set up. So here is the setup. This is a disk in the plane. You fix delta positive. You discretize this disk with the triangulation of mesh delta. And you fix 2 points which are neighbors on this small lattice, and they are close to the origin. And what you want to know is the probability that the following happens, that out of one of these vertices, there's a black path going all the way to the boundary, and out of the other one, there's a path of the other color going also to the boundary. And of course, these paths have to be disjoint because they have different colors. So of course, here I'm using a fixed disk and mesh delta. It would be exactly the same to put a fixed lattice and take the disk larger and larger. And so if you do that, you find that n here and 1/delta here, they play exactly the same role. So given that the existence of one curve from the center to the boundary behaves like a power, you might think that 2 paths from the boundary, from 0 to the boundary, this should also behave like a power. And so it's the case that this behaves like delta to the power 1/4. And still plus little o of 1. And as it turns out, this one will be a little bit easier to compute using SLE because it's somehow because it's more symmetric. Okay, so how to relate this to SLE? So the first remark And it's something a little bit technical to do, but it's classical from Rousseau-Seymour-Welch. There's something called the separation of arms lemma, which says that on this event that you have two arms of different colors going from the origin to the boundary, so conditionally on that, with positive conditional probability, these arms land on separated bits of the boundary. They cannot really land very close to each other, because that would make it very difficult to extend. And essentially, by Rousseau-Seymour-Welch, if you have some estimate on the rates of decay of this probability, well, you can show that if you have arms, they have to be a little bit separated. And from that, in fact, what you can look at is the probability that this happens, that the blue arm here has to connect to the bottom of the boundary, and the red arm has to connect to the top half of the boundary. So we can prescribe boundary arcs for the arms, in the sense that we can ask that each arm goes in the prescribed deterministic interval on the boundary, and the probability that we get for this event with additional constraints to exit on these pieces of the boundary, they have the same probability as the unconstrained one up to a constant. So they get the same probability up to constants which essentially come from the Rousseau-Seymour-Welch theory. So that's the first step. It's nice to be able to ask for these paths to exit at prescribed locations, because now this is looking a little bit more like the setup of SLE. We have a domain and we have now points on the boundary. And just to finish the picture, to make it look a little bit even more familiar and connected to the first course last week. So this will be the picture. We have a domain with two boundary arcs of two different colors. We want two neighboring points inside to be connected to these two arcs here. Okay, the second remark is that this event, now that these 2 points are connected to these two halves of the boundary, you can tell if it's happening or not by looking at the exploration process. So if you wanted some explorable event, so what do? You start your exploration process here. So it's exploring, having red on the right and blue on the left. So you do something like this. You explore the boundary between the two clusters of the boundary. And it's easy to see that if these arms exist, the exploration process, it has to go through the center. So it has to approach here, and then it does whatever it wants. And vice versa, if the exploration process does go through this edge between the two vertices, then, well, automatically the boundaries of the exploration, they contain paths of the right color. So this probability, the probability of this event here, is the probability that the origin is on the exploration process. So here gamma will be the exploration process. And this two-arm event is exactly the event that the curve gamma here goes through the origin. So now we can start hoping to have something using SLE, because we know that as delta goes to 0, this interface gamma, it converges to SLE6. So essentially, this 1/4, it describes the probability that SLE goes through one particular point in a domain. So that was just for motivation. I will not use exactly SLE in this frame here, because the computation is harder in this case and it's harder to generalize. But at least as motivation, if you have an SLE, if you have this picture here, the events that you have these two arms, it should be related to SLE. So remember we had this radial, So yesterday we defined one particular version of SLE, which was a radial SLE. And the radial SLE doesn't go from one point of the boundary to another, but it goes from one point of the boundary to the inside of the domain. And it was defined by solving the equation that dt gt of z was gt of z times gt of z plus e to the I beta t divided by gt of z minus e to the I beta t. Yes. Okay, so this is an SLE, and I told you that it's related to the chordal SLE in the sense that they are absolutely continuous with respect to each other as long as it makes sense. And I also said something that comes out of the proof, that they are exactly the same. So up to the separation time for kappa equal to 6. So I told you this, I didn't give you the proof, but it comes from a computation of Giersanov type, that if you want to compare them, well, the absolute density of one with respect to each other is constant equal to 1 because you can compute it. So the point here is that if you are studying this event, and if you go through this point here, it has to occur before you separate the point from the target of the SLE, because once you separate the points, the exploration curve will continue towards the -1 point here, and there's no way it can go through 0. So this event, somehow it's also measurable with respect to a radial SLE. So that was all for motivation, but now let's go right into the computation for radial SLE. So I will come back to the motivation and to the link with percolation just at the end of this lecture. So today I want to compute the arm exponents for radial SLE. And I will do that for kappa between 4 and 8. And you will see exactly why. Well, if you remember the transition at kappa equal to 4 and transition at kappa equal to 8, it's natural to look at this value of kappa. Okay, so this is the setup now. So we have a disk, we have 0, we have 1, and we launch an SLE from 1, which is a radial SLE for kappa bigger than 4, so it does something like that. And to match this event, what I will do is I will fix some epsilon positive. I will fix a disk around 0 of radius epsilon, and I will follow the SLE until it touches this small disk around 0. So until this time here. So T sub epsilon is the inf of times such that gamma T is on the circle around 0 of radius epsilon. So it's exactly this stopping time here. So if you wish, you will think about it as following the exploration of percolation until you reach a neighborhood of 0. But of course, well, the exploration of percolation is the chordal case, so we'll come back to that later. But for now, you need to have this in mind, that this is some interface or some modification of an interface that we are following to a certain scale epsilon. So this arm event, it corresponds to the fact that the exploration here does not disconnect 0 from some point -1 on the boundary. Okay, so the statement is this, that I want to prove. The probability that gamma between 0 and t epsilon does not separate 0 from -1. So this is what I will call the non-disconnection event. This behaves like epsilon to a power, so power alpha of kappa plus equal O of 1, and alpha of kappa is kappa minus 4 over 8. So that's what we want to prove, and just to connect that to percolation, if you plug kappa equal to 6 here, well, you get 6 minus 4, which is 2 over 8, which is 1 over 4. So the alpha of 6 is 1 over 4. And this 1 over 4 is the same as the 1 over 4 that is over there. So that's what we want to know. We want to estimate this probability, and we want to say something about how it decays as epsilon goes to 0. Okay? So first remark. The first remark is something I mentioned already yesterday. It's the Kuber 1/4 theorem. Remember that the time parameter is given in terms of the conformal radius. And the conformal radius of omega t, so the complement in the disk of the curve up to time t, this is normalized to be exactly e to the minus t. That's the definition of the time parameter for radial SLE. But on the other hand, the conformal radius is up to constant. It's the same as the distance between 0 and the boundary of omega t, up to universal constants. So if you apply these results here from complex analysis at the time t epsilon, well, the distance between the origin and the boundary, you want to say that it's exactly epsilon, because that's on the event that you don't disconnect at time t epsilon. Okay, now this is the, okay, it's the first eating time of this radius epsilon. So at this time, you are at distance epsilon. That's just the definition. So the distance here is epsilon, and this is e to the minus t sub epsilon. So what you get is that t sub epsilon is actually log of 1 over epsilon plus big O of 1. And this big O of 1 is really bounded by universal constants, which don't depend on anything, like log of 4 and log of 1 over 4, something like that. So this looks like a statement at stopping time, but really you can see it as a statement at a deterministic time, which is log of 1 over epsilon. And that will be very useful. Okay, the second thing is, so remark number 2, which will give us the way to set up the computation. What happens at the moment when the curve disconnects 0 from minus 1? So at the disconnection time, what do we have? We have, so this is our domain, this is 0, this is 1, this is minus 1. We start the SLE from 1. It does something complicated. And at the disconnection time, something like that happens. That's, well, you disconnect 0 from minus 1. That's the definition of this disconnection time. It can happen by touching the boundary. It can also happen by touching the previous boundary of the curve, and it will not matter so much. But now we'll do the same kind of remark we did for the phase transition at kappa equal to 4. If you look at what happens just before you disconnect, Well, what is happening now? We are looking at this curve growing towards 0. So let's map the whole picture by the conformal map, which is g at disconnection time. I'll call it tau. Tau minus eta. And eta is very small. So g tau minus eta maps the complement of the curve back to the unit circle, like this. It maps the tip here. This is the tip, gamma times tau minus epsilon. It maps the tip somewhere. Let's say here. So this is e to the I theta at time tau minus eta. And now there's one more point which is interesting, which is -1. So the question is, what happens to g tau minus eta of -1? So I will redo the argument that I did already for the chordal SLE case at kappa equal to 4, just because it's something nice. But the thing is, we want to show that in the image, -1 is mapped to something which is very close to gamma of tau minus epsilon. So the idea is to prove that g tau minus epsilon of -1 minus e to the I theta tau minus eta, this is small. This goes to 0 as eta goes to 0. So how do you do that? Well, you say that we will look at the harmonic measure from 0 of everything that is on this side here. So everything that is on the outside of the bubble, from the tip all the way to -1. So this whole boundary arc here and we want to show that this arc is mapped to something very small by the GT. But to do that, well, we'll just say that we look at the harmonic measure of this from 0. So omega in omega t from 0 of the blue part of the boundary. And we have two ways to estimate that. Well, first we say that it's the harmonic measure, it's the probability that the Brownian motion started here will touch the blue part before it touches the rest of the boundary. And so it has to go through this very small opening here. And so it's small. It's small because there is a small opening. But on the other hand, if you look at the image here, so let's do it in the right direction. So you turn clockwise to go from this to -1. I claim that if you look at g tau minus eta of -1, it's very close here. And the reason is that the harmonic measure is conformally invariant, because the Brownian motion is conformally invariant. This is a conformal map. So this harmonic measure of the blue curve here in this domain is the same as the harmonic measure in the disk, also from 0, of the arc between e to the I theta tau minus eta up to g tau minus eta of -1. So of this directed here part of the boundary. Okay? So this is just by conformal invariance of the harmonic measure, which is the same as the conformal invariance of Brownian motion. And the last part of the argument is to say that now it tells us that the harmonic measure on the circle, that's exactly the same as the Haar measure on the circle. It's the same as the Lebesgue measure divided by the total length by rotational symmetry. So this harmonic measure here, this is just the length up to 2 pi, is the length of this interval here. So this is exactly the same. Well, up to a small constant which comes from the curvature, but it's the same as g tau minus eta of minus 1 minus beta at tau minus eta, minus e to the I theta at this time, divided by 2 pi. So this is because the harmonic measure is uniform, and then this is almost a straight segment. So you can estimate it by the Euclidean distance. So we know that this is small, it's equal to this. So in particular, we know that this minus this goes to 0. So in particular, we know that g tau minus eta of minus 1 minus e to the I theta at tau minus eta, it goes to 0 as eta goes to 0. So you see, it's exactly the same idea as we did to see if the chordal SLE was going to the boundary of the domain or not. We say that just before it does, the harmonic measure of something on the boundary has to go to 0 because of the geometry. And on the other hand, this harmonic measure is equal to the value of some process or something about the driving process. And that tells us that the driving process is doing something. Okay, so this is the key remark. So now we will look at this process a little bit more closely. So we will look at Zt, which is the ratio between these 2 points. So it's e to the I theta t divided by gt of minus 1. So what we just proved here is that Zt, as t increases to the disconnection time, well, the difference between the two of these terms goes to 0, but they are all modulus 1. So this goes to 1 as t goes to tau. Okay, and on the other hand, we start from somewhere. We start from z0, which is, let's say it's minus 1. So we have this process. It lives on the circle. It starts from minus 1. And at the time we are interested in, it goes to 1. Okay, next transform to make things even a little bit nicer to draw and to compute. We'll define yt to be the argument of zt. So it's the continuous determination of the argument of zt, and zt depends continuously on t, so there's no problem defining this. And we define the argument, and we will impose that this is between 0 and 2 pi. So there's a unique definition of the argument of zt between 0 and 2 pi. For the moment, take a close interval. So this is a process which lives in 0, 2 pi. And the moment that zt reaches 1 is exactly the moment where yt reaches either 0 or 2 pi. So yt, as t goes to tau, it goes to either 0 or 2 pi. And you can check that whether it's 0 or 2 pi depends on the direction in which you close the loop around 0. So here in this picture, it's one of them. And if I tell you which, I will get the wrong answer, but it's one of them. But if you close the loop in the other direction, well, gt will approach from the other direction, and the y will approach the other end of the interval. Okay, and then the last remark is that because of this remark and the definition of the stopping time, essentially the probability we want to compute, so the probability that you have non-disconnection at t epsilon, well, that's the probability that the disconnection time is bigger than T epsilon, tau bigger than T epsilon. And now we have a characterization of tau in terms of the behavior of this yt here. And on the other hand, T epsilon is something like log of 1 over epsilon. So this is the same as the probability that tau is bigger than log 1 over epsilon. And now, since tau is the heating time of 0 or 2 pi by the process yt, this is the probability that yt remains in the interval 0, 2 pi, in the open interval, so without touching the boundary, up to t equal to log of 1 over epsilon. Okay, so this is the final setup that we arrive at. The probability that we want, which will tell us the probability that you have arms for the configuration intercalation, the probability that the geometry of the SLE is what we want. You can restate it as some probability about this process yt, and it's a survival probability of a process in the interval. Okay, so now the rest of the root is very classical. It's some kind of Feynman-Katz formula, or something like that. So we have this process yt. It lives in an interval, and we want to compute the probability that it survives without touching the boundary for a given time. And this given time is going to infinity as epsilon goes to 0. So one computation, if you look at the definition of yt is just the argument, so it's computed using the log of zt, and zt is the ratio of these two processes. Theta, you know that is square root of kappa times the Brownian motion. Gt follows the Loewner equation, so you can do the computation and use the Ito formula. And it will tell you that dyt is square root of kappa dbt plus something which will be proportional to the cotangent of yt over 2 dt with a factor in front which I don't want to get wrong, which is a simple function of kappa. And it is exactly it's 1. So it's a very simple function of kappa. Okay, and this cotangent is the ratio of sine and cosine, so it comes from the harmonic measure computation. Okay, so we have this very nice diffusion. And by the way, one way to remember that the constant is 1 is to look at the local behavior at 0. And at 0, you get the square root of kappa times dbt, which is the Brownian term. And here you have something like 2 over yt. So locally at 0 is the same process we used for the kappa equal to 4 phase transition. So this is the process that you get. So it's a process in the interval, and what we want is the probability starting at pi. So that's the initial point where yt is starting, because you compute this at t equal to 0, and you get z0 equal to -1. That you survive up to time log of 1 over epsilon. Okay, so the next step is, now we have one process which lives on the interval, and so it has a generator which is kappa over 2 times the Laplacian plus this times the derivative. So there is L, which is the generator of this, of yt. And if you can find an eigenfunction for this generator which is positive, It will have to be the leading eigenfunction. It will give you the leading eigenvalue for the generator. And the leading eigenvalue will give you the exponential rate of decay of the survival probability. So it will be enough to find a positive eigenfunction of L kappa, and then the eigenvalue is the same as the rate of decay of this probability. So this, let's call it little p of log of 1 over epsilon. And this eigenvalue will be the rate of decay of p of t.
So you use the Schramm-Loewner here?
Yes, you use something like that to say that you can compute the whole spectrum and all the eigenvalues are simple and everything. This operator is very nice.
That is positive eigenvalue, eigenfunction.
Yeah, there is a unique positive eigenfunction. The rest are orthogonal to it. And you can, so if you can find one, it's the right one. And as it turns out, there is an explicit eigenfunction which is positive. And this eigenfunction is sine of x over 2 to the power b of kappa with an exponent b of kappa, which is, since it's not 1, I want to get it right, so it's somewhere in the notes and it's hidden. It's 1 minus 4 over kappa. And if you plug this into the sign and you do the computation here, what you find is that the eigenvalue is this alpha over kappa, which is kappa minus 4 over 8. Maybe with a minus sign. So this is all a computation, is just differential computation. You look for an eigenfunction of kappa over 2 Laplacian plus this times the derivative, and you find that sine to the power of b of kappa with this b of kappa, well, it's positive on 0 2 pi, obviously, because the sign is positive, and it's an eigenfunction. So now you can unroll everything. The alpha of kappa is this. It gives you the rate of decay of this probability. So what you get is that this behaves like e to the minus kappa minus 4 over 8 times the log of 1 over epsilon. And that's it. That's what you want to get. If you then take the log down, what you get is exactly the epsilon to this alpha of kappa. So this alpha of kappa is minus alpha of kappa, if you want. The alpha of kappa here is positive. Okay, so this is the setup, and this is the way you compute these probabilities. And you get the exponents as eigenvalues of particular differential operators, which are generators of things related to SLE. And as you can see, there is nothing very special about kappa equal to 6 here. There is something special about kappa between 4 and 8. At least with kappa positive, because you want all these to make sense. So you want the process to die, you want the eigenvalue to be of the right sign. But there is nothing exciting happening at kappa equal to 6 in this computation. So just one remark. So kappa equal to 6 gives you an alpha of kappa, which is 1 over 4, and it gives you a b of kappa, which is 1/3. And if you want this b of kappa, this 1/3, you saw it already in the computation of Caddy's formula. It comes from the fact that if you map the upper half plane conformally to the triangle, to the equilateral triangle, well, the behavior here at a point where the boundary is flat, this is 0. This is the image of 0. You want to divide the angle by 3. So the local behavior of this map is, this is phi. Phi of u at 0 behaves like u to the power 1/3. And this 1/3 is the same as the 1/3 that you get here. So it's really something about the boundary behavior of the percolation process. It's the boundary behavior of Cardy's formula. And it's also related to another 1/3, which is the one-arm exponent in a half plane, which tells you that the probability that this happens, that you start at distance delta and you reach distance 1 by an open arm, so the probability that this happens for critical percolation, this also behaves like delta to the 1/3. So this 1/3 is really occurring at many places of the study of percolation, and it's always the same 1/3. It's always because Cardy's formula is obtained by z to the 1/3 locally. Okay, I still have something like 15 minutes. I want to tell you how to get the 5/48 from SLE. And the last thing I want to do is to tell you how to start from these SLE computations and obtain really something about the discrete behavior of percolation. So first about the 5/48. So about 5/48. So it will be essentially one big picture. And the picture is the following. Look at what happens if you follow the exploration process. And I will have to cheat a lot in the picture because I don't want to make all these choices when you close loops, etc. But look at this picture. This is an exploration process that closes a loop in this direction, and then it closes a loop in the other direction. Something like that. So if you have good eyes, you will see that separating the origin from the boundary in this picture, you have one blue loop, which is this, and you have one red loop, which is this. Here. So each one corresponds to a disconnection between 0 and the boundary of the domain. But depending on the direction in which you close the loop, it will be of a different color. And that's because if you turn on the left, it's your left side that will separate, and if you turn on the right, it's your right side that will separate. So what it means is that if you want to look at the disconnection time, which is what we just did here, by the SLE exploration, any direction will work. Any direction will, by definition, it will separate 0 from the boundary. But now if you want to look at the probability that there is an arm, there is a blue arm, this is the probability that there is no red loop. Because of the duality in percolation, the only thing that can prevent a blue arm is the presence of a red loop. And this is exactly saying that there is, it's a probability that there is no, and here you can check that the red will be counterclockwise. So there is no counterclockwise loop in the exploration. So before we were looking at any closing of a loop. Now we want to just prevent loops in one direction, because the others, they will not prevent the existence of this particular color. So then you do the same computation, you do this, you follow the track all the way to here. And remember I told you here that yt at the disconnection time, it goes to 0 or 2 pi depending in which direction you close the loop. And here, we just want to prevent one loop direction. So this will be the probability that yt does not hit 0 by time log of 1 over epsilon. But it is allowed to hit 2 pi, because hitting 2 pi will not prevent you from having an arm. And so if you want to do it properly, you get a process yt, which is the same process. It has the same generator because the computation is the same. It lives in the interval. It's skilled at 0 and it's reflected at 2 pi. So now yt is reflected at 2 pi. And so you arrive here, and what you're looking for really now is some eigenfunction. Here we wanted that the eigenfunction to have boundary value 0 because that's the killing at the boundary. Now we want some eigenfunction of the same generator but with the boundary condition that is 0 at 0 and it's Neumann boundary condition. So derivative 0 at 2 pi. So we want to find phi such that phi of 0 is 0, phi prime of 2 pi is 0, otherwise phi is positive inside, and L phi is minus something times phi. So all that changes if you want to go from 2 arms to 1 arm is the boundary condition corresponding to the event that you don't want to exclude anymore. And so you replace the Dirichlet by a Neumann boundary condition. So you do exactly the same kind of computation. You do the same prediction of an eigenfunction. You know a priori that the exponent here, which describes the local boundary behavior of the function, will have to be the same because it's the same one-third for all percolation events. And it turns out that here, the phi that you get is the sine of x over 4 to the power b of kappa with the same b. And here you can check that this at 2 pi is the sine at pi over 2, so it's locally constant. Its derivative is 0. So it has the right boundary condition. So you do that, and then you plug that into the computation. You compute the image of this by L, and this will give you the value of the exponent. And this is the thing I wrote yesterday, which tells you that the probability that the first counterclockwise loop of a radial SLE kappa, probability that this happens after you hit distance epsilon, that this behaves like epsilon to some exponent which is a rational fraction of kappa, which is the one I wrote yesterday and which I never remember by heart, but it is equal to kappa squared minus 16 over 32 kappa. So again, this is the leading eigenvalue of some operator on a space of functions with appropriate boundary conditions. And you can check that as kappa equal to 6, you get the alpha tilde of kappa, which is 5 over 48. So that's where this mysterious 5 over 48 comes from. That's just some eigenvalue of some operator which is related to SLE. Okay, I still have 5 minutes, and in 5 minutes I hope to be able to tell you now how to get a proof of this result. So what do we have? We have that we know how to compute the one-arm probability or the non-disconnection probability or the equivalent for the SLE. And we know that the percolation exploration converges to SLE. So what do we have? We have that the probability that if you look at percolation in an annulus with mesh delta, so this is the mesh, this is little r, this is the small radius, this is the big radius. We know that the crossing probability for percolation here, it converges to the counterpart for the scaling limit of percolation, which is what we just derived, which is the probability that in this domain, the radial SLE, well, let's use a different color for the SLE because that will be, so the dual was red. So the probability that the radial SLE closes only clockwise loops before it arrives at epsilon. So because of the link between percolation and SLE, which also extends in this radial setup, but I have no time to really do the details, but it's believable at least. So this probability, as delta goes to 0, it converges to the same probability in a radial SLE, and we just rescale everything so that the disk is the same as the one for radial SLE. So from 1 to the radius, which is little r over big R. So that's the limit. And so let's do something a little bit more precise. So this is F delta between R and R. This probability for percolation on the delta grid in an annulus between R and R. This converges to this function f of little r over big R. So this is Smirnov's result about convergence. And now what we just did was to look at the behavior of this function f as the ratio between the radii goes to infinity. Because that's what we got by looking at the expansion here as epsilon goes to 0. And what we get was that this behaves like r over r to the power 5 over 48. Okay, and the question is, how does this imply that the behavior of this between the microscopic radius and the radius 1 also has the same exponent? And it's not completely clear a priori, and that's the whole difficulty if you want to find the exponent from the statement of Cardy's formula, that you want something about the microscopic radius and you have information about the scaling limit, which is at the macroscopic radius. And so there is one ingredient missing, and which is the key. And the key is called quasi-multiplicativity. So I have very little time to give you the details, but I will just tell you how it works. Maybe I'll do the picture in the one-arm case. So here's the first statement is that whenever you have R1 less than R2 less than R3, you can look at the annuli between R1 and R2 and the annulus between R2 and R3, and they are disjoint. So the percolation in these annuli, it's completely independent. And on the other hand, if you cross between the small one and the big one, you have to cross between the small one and the intermediate one, and also from the intermediate one to the big one. So in terms of probability, it tells you that F delta between R1 and R3 is always less than F delta between R1 and R2 times F delta between R2 and R3. So this is submultiplicativity of the probabilities, and it's just from inclusion and independence between disjoint annula. So this is essentially it's trivial. And the quasi-multiplicativity tells you that, in fact, there is also a lower bound, which is constant times the same product. With C here, which is positive and it's universal. It only depends on the event you're looking at. So here, the number of arms, if you want. And the way you prove that is essentially using Rousseau-Seymour Welch. And the argument looks like that. If you go from the small radius to the radius here, and if you go from this radius to this radius, the only thing you need is to connect this path to this path. And to do that, what you can do is look for a device which is something like that. A pair of circuits in some intermediate annulus of fixed ratio. So the device is the blue part of the picture. It has two circuits and one crosscut here, arranged in such a way that the small circuit has to intersect this arm here, and the large circuit has to intersect this arm here, and the crosscut connects the two. And this exists with positive probability by the Rousseau-Seymour Welch estimates. And C is essentially the probability that there is this device at the radius you want it. So this is how you get the quasi-multiplicativity for the one arm probability. If you want to do it for the several arms, you need separation of the arms, and it's a little bit more technical, but the idea is exactly the same. Okay, so now the only step missing is just a statement of quasi-multiplicativity and doing something proper and counting the epsilons. So let's fix, we want to look at f delta between delta and say 1. Okay, and I will fix for the moment k, which is much bigger than 1, but it's fixed. And what I will do is I will write this event as events between delta and 1, but going through the radii which are delta times k to the something. So the picture is like this. So this is delta k, this is delta k squared, and this is 1, which is delta times k to the something like log over 1 of delta divided by log k. Okay, it's the number of scales k that you can fit between the microscopic radius and the macroscopic radius. So because of the quasi-multiplicativity, this behaves, so let's call this n here, the number of scales. The number of times you use this is the number of scales, so you are hit with some c to the power n times the product of the f deltas between delta kl and delta k L plus 1. And now, because of the statement of the scaling limit, for fixed k, as delta goes to 0, this is just the crossing probability in a big annulus between delta kl and delta kl plus 1. So this, each individual term here converges as delta goes to 0 to exactly f of 1 over k, f of k. F of the ratio between the two radii here. So it's the same limit for everything. It converges as delta goes to 0. And the number of terms is exactly n. So all the terms converge as soon as they are macroscopic. So as soon as the L is positive. Just the first term, when you want to go from the microscopic to k, this is where you don't have any information. So you plug that in a constant, and what you get is that this is like f of 1 over k to the power n minus 1 times some constant to the power n. And this constant is universal. Okay, now we are writing everything in terms of f, so we know that the f here behaves like r over r to the 5 over 48. So this behaves like k to the minus 5 over 48 to the power n minus 1, c to the n. And now you remember that the definition of n was the log of delta divided by log of k. So this product, let's put this minus 1 here. This is exactly the same as n as the radius to the power of 5 over 48. So this now is delta to the 5 over 48 times universal constant to the power n. And this n, again, it's something like a constant times n, which is the log of k. So what you can do is you can plug it here, plus eta. And eta is the log of c. So that's the bound that you get. And you can make the eta as small as you want by taking k large enough. Because then you divide by log k, and this eta is essentially the universal constant divided by log of k. So that's it. That's how you start from the SLE estimates, and from them you can derive estimates about the discrete behavior of percolation. And just one open question. Which is natural here. The open question, so two open questions. The first one is to show that the probability f delta of between r and r divided by the limit, this r of r to the power alpha, show that this is bounded. Here we get delta to the right exponent, but the little o of 1 is on top, so the ratio is not bounded. We get a very bad bound. And what we lose happens at the microscopic level. So going from this to a constant in front is really something about the local behavior of percolation. It's some understanding that is still missing. And the second open question, which I like very much, is now look at the probability that instead of having one blue arm and one red arm, you look for two arms that are of the same color, but disjoint. And the question is, does that behave like some exponent of delta, and if so, which one? And this, if you want to address that by using SLE techniques, it fails very quickly, because you cannot really explore the existence of two arms of the same color using an exploration process. Okay, I guess that's all I wanted to do in this course. So, thank you. Any questions?
What would need to be done to get rid of the little o of 1 in the exponent?
Well, you need to push this estimate to constants down to the microscopic level.
Yes. So
it's
what are the difficulties in
that? We have no idea. We know the limit, but we don't know how you approach the limit. So if you get very precise estimates about the speed of convergence of the crossing probabilities that are good enough, they will improve this. But it's not even clear how precise you need the speed to be. I mean, powers of the size, this is not enough. You need very detailed behavior at the microscopic level.
So for this function f, you don't have more precise asymptotics?
Oh, the f without the delta, we know it explicitly.
Okay.
But the question is about the convergence here. Now, this f is explicit. It's you do the expansion in eigenvalues and you compute, and it's this here. This is up to constant. So the difficulty is here, it's not here. And it's not a question about the f, it's really a question about the discrete model. Yes?
Intuitively, what does it mean for kappa equals 4?
That it doesn't go to 0. You get exponent 0.
Yeah, so there's a log correction,
Is there a log correction?
or just
No,
disconnect?
it's a simple curve, so the probability that you don't disconnect is 1.
Oh yeah, no,
So-
that's stupid.
So you don't really see the log at this level. You will see it if you want to state something about the chordal SLE
Oh, that's fine.
using radial estimates, because
Yeah.
then you get the log, but the log is not there. It's in the random Nicodean derivative of the 2. No, nothing magical, nothing log here. It's
Yeah.
really one-dimensional computation. Okay, I guess it's time for coffee.